A warm welcome to part 7 of the lecture on functions. In the previous lecture, we had started discussing about periodic and aperiodic functions. In this lecture, we shall continue our discussion on the same topic. Let me begin by making a couple of preliminary comments about the content in the previous lecture. We showed that if P is periodic with period t, that is f of x plus t is equal to f of x for all x belonging to R, then f is also periodic with period nt, where n is a natural number. That is, f of x plus nt is equal to f of x for all x belonging to R. However, we can say something more. If f is periodic with period t, then not only f of x plus nt is equal to f of x, but also f of x minus nt is equal to f of x for all x belonging to R, where n is a natural number. So in general, what we are saying is that if f is periodic with a period t, then f of x plus zt is equal to fx for all x belonging to R, where z is any integer, not necessarily a natural number. We'll see a quick proof of this for the case when n is equal to 1. So f of x is equal to f of x minus t plus t. But now since t is a period, this is simply equal to f of x minus t. So we have proved that f of x is equal to f of x minus t. For the general case, you can resort to the principle of mathematical induction. Let me also make a comment that while we introduced the concept of periodicity, we defined it only for functions from R to R. However, this is not a strict requirement. You can have periodic functions defined on subsets of R, but those subsets need to be of a special kind, the so-called T-translate invariant subsets. But we will not go into the details of such kind of functions. We will only be concerned with periodic functions defined from R to R. In the previous lecture, we defined formally what a periodic function meant. So it's good time to see what an aperiodic function is. Basically, any function which is not periodic is said to be aperiodic. And the essential feature of an aperiodic function is that there is no repeating pattern after any regular time interval. Let us see some aperiodic functions. The simplest example is the identity function, x maps to x. Why is this function aperiodic? Let us prove it. Suppose it is not aperiodic. Then it must be a periodic function. That means there exists a t greater than 0 such that identity of x plus t is equal to identity of x for all x belonging to R. This follows simply from the definition. But this means that x plus t is equal to x for all x belonging to R, which implies that t is equal to 0. Now, this is a contradiction because a period necessarily has to be positive. So the conclusion is our assumption that the identity function is periodic is false, and hence the identity function is aperiodic, which is exactly what we wanted to show. If you look at the graph of the identity function, it is just a straight line passing through the origin, and clearly there are no repeating patterns after any time interval, say capital T. So this function, even graphically, you can conclude that it is not a periodic function. Now let us look at a second example, f of x is equal to x square. Our claim is that f is an aperiodic function. Let us prove it by contradiction as in the previous case. Suppose f is periodic. Then there exists a t greater than 0 such that f of x plus t is equal to f of x for all x belonging to R. And t must be a constant. Remember that this was an essential remark made in the previous lecture, that t must be a positive constant. So now it follows that x plus t the whole square is equal to x square for all x belonging to R. Now this simplifies to x square plus t square plus 2tx equal to x square, which means t square plus 2tx is equal to 0. If you take t common, you get t into t plus 2x equal to 0, which can only be satisfied if either t is equal to 0 or equal to minus 2x. Now in both of these cases, t cannot be a period because t equal to 0 is unacceptable because of this assumption, and also t must be a constant. Here t is equal to minus 2x, which is not a constant. It depends upon the value of x. So we can conclude that again our assumption that fx equal to x square is periodic is a false assumption, and hence by contradiction we have proved that f is indeed a aperiodic function. Let us take one more final example. Let f be a function from R to R defined in the following way. F of x is equal to sine x when x is greater than equal to 0 and cos x when x is less than 0. Now the question is f a periodic function? I urge the viewer to prove it himself rigorously that f indeed is an aperiodic function. As a hint, what I'll mention is the following. I have drawn here the graph of f. So for x greater than equal to 0, the graph of f is that of the sine function, and for x less than 0, the graph of f is that of the cos function. Now my claim is that f is an aperiodic function. So even though I am not going to prove it rigorously, but I can give you a subtle hint. Assume that f was a periodic function. In that case, we know that a regular pattern repeats itself after a fixed interval of time. Now if you look at the graph carefully, you see that there is a jump discontinuity at the origin. Now if this function were to be periodic, the same kind of jump discontinuity would have occurred after some fixed intervals of time. But that is not the case, as you can see. So that gives you an indication that the function is not a periodic function. As again, I would urge the viewer to prove it more rigorously. Now we move to a more subtle and intricate topic, namely the sum of periodic functions. And let me at the outset mention that whatever we are going to do in this particular subtopic will in general be also true for the product of periodic functions, even though we will mostly be restricted to sum of periodic functions. The general situation here is quite complex. Let me start with making some comments. Let f and g be periodic with periods t and s respectively. If there exist natural numbers n1 and n2 such that t by s is equal to n1 by n2, that is, n2 into t is equal to n1 into s, equal to r, suppose. So I'm calling this common product r. Then the claim is that r is a period of f plus g. Let us see a proof of this. F of x plus r plus g of x plus r is equal to f of x plus n2t, because r is equal to n2t, and also r is equal to n1s. So f of x plus r plus g of x plus r is equal to f of x plus n2t plus g of x plus n1s. But since t and s are periods of f and g respectively, this is simply equal to fx and this is equal to gx. So f of x plus r plus g of x plus r is equal to f of x plus g of x. Thus we conclude that r is a period of f plus g. So if t and s are periods of f and g such that t and s have a common multiple, say r, then r must be a period of f plus g. Let us see an example. Consider f is equal to sin x and g is equal to sin 2x. Clearly, f has a fundamental period of 2 pi and g has a fundamental period of pi. And 2 pi is a common multiple of pi and 2 pi. And so is 4 pi, 6 pi, 8 pi, and so on. I want to show that 2 pi and also 4 pi, 6 pi, etc. are periods of the function f plus g. So f plus g x plus 2 pi is equal to f of x plus 2 pi plus g of x plus 2 pi, which is sine of x plus 2 pi plus sine of twice x plus 2 pi. And this is equal to sine x plus sine 2x, because 2 pi is a period of sine and 4 pi is also a period of sine 2x. So finally we conclude that f plus g of x plus 2 pi is equal to f plus g of x. Hence, the conclusion is that 2 pi is a period of f plus g. It can also be shown that in the previous example, 2 pi is in fact the fundamental period of f plus g. Now this brings us to an important question. If f and g are periodic with fundamental periods t0 and s0, and suppose r0 is the LCM of t0 and s0 if it exists, we will see later an example when the LCM does not exist. Then the question is the following. Is R0 necessarily the fundamental period of f plus g? The answer in general is no, and we will provide two strong counterexamples for it. The first one is the simplest one. Let f be equal to sine x and g be equal to minus sine x. So clearly the fundamental period of both f and g is 2 pi, and the LCM of 2 pi and 2 pi is obviously 2 pi. However, is 2 pi the fundamental period of f plus g? No. Why? Because f plus g is sin x minus sin x, which is 0, and 0 is a constant function. And the constant function, as we have already seen in the previous lecture, does not admit a fundamental period. So clearly, 2 pi is not the fundamental period of f plus g. Let us take another example. Let f be equal to mod of sin x and g be equal to mod of cos x. I have drawn for your sake the graph of mod sin x and mod cos x. Clearly both mod sin x and mod cos x are periodic functions with fundamental period equal to pi. And clearly the LCM of pi and pi is equal to pi. We want to ask the question that is pi a fundamental period of f plus g? The answer is again no. Let us see why. Consider f plus g of x plus pi by 2. Now f plus g of x plus pi by 2 is equal to mod of sine x plus pi by 2 plus mod of cos x plus pi by 2. Now sine of x plus pi by 2 is cos x, and cos of x plus pi by 2 is minus sin x. And because of the modulus sign, you can forget about the minus part. So finally, it boils down to mod cos x plus mod sin x. And this is nothing but f plus g of x. So we have clearly seen that pi by 2 is a period of f plus g. And since pi by 2 is a period of f plus g, then pi cannot be the fundamental period of f plus g, because by definition fundamental period is the smallest positive period of the function. In fact, we can show that pi by 2 is the fundamental period of f plus g in this case. The graph of mod sin x plus mod cos x has been shown, and you can clearly see that pi by 2 is the fundamental period, as it is the smallest time period after which the pattern repeats itself. This brings us to an important conclusion. If R is the LCM of T0 and S0, where T0 and S0 are the fundamental periods of the functions f and g respectively, then R is definitely a period of f plus g, but not necessarily its fundamental period, as we have seen in the last two counterexamples. Now we ask another important question. If f and g are periodic with fundamental periods t0 and s0 respectively, is f plus g necessarily periodic? The answer is again no. The sum of two periodic functions can in fact turn out to be aperiodic. Let us see an example. Consider f is equal to sin x and g is equal to sin pi x. Then f plus g of x is equal to sin x plus sin pi x. Sin x and sin pi x have fundamental periods 2 pi and 2 respectively. Now, is sin x plus sin pi x periodic? The answer is no, and we will prove it by contradiction. Suppose sin x and sin pi x is periodic with period t. then this implies that sine x plus t plus sine pi of x plus t is equal to sine x plus sine pi x for all x belonging to R. Call this equation 1. We differentiate 1 twice with respect to x to obtain the following equation. Sine x plus t plus pi square sine x plus t into pi is equal to sine x plus pi square sine pi x. Now this implies sine x plus t minus sine x is equal to pi square into sine pi x minus sine pi times x plus t. From equations 1 and 2, we can deduce the following. Sine pi x minus sine pi into x plus t is equal to 0. But from equation 1, sine pi x minus sine pi x plus t is equal to sine x plus t minus sine x. Therefore, it now follows that sine x plus t minus sine of x is equal to sine pi x minus sine pi times x plus t is equal to 0. Therefore, sine x plus t must be equal to sine x and sine pi times x plus t should be equal to sine pi x. Call these equations 4 and 5. From 4 and 5 we can conclude that t is a period of sine x and sine pi x both, which means that t must be of the form 2n pi and 2m simultaneously, where n and m are natural numbers. But that is a contradiction because t simultaneously cannot be an irrational number and a rational number. Therefore, we conclude that the function sin x plus sin pi x is an aperiodic function. Let me end this lecture by stating a very astonishing result, which is the following. A polynomial of degree n, strictly greater than 0, can be expressed as a sum of n plus 1 periodic functions. Now, this is quite a remarkable theorem because it is in no way intuitive why a polynomial of degree n can be expressed as a sum of n plus 1 periodic functions. The proof is beyond the scope of our discussion since it involves viewing R as a vector space over Q, which is an infinite dimensional vector space, and then considering its Hamel basis and stuff. All those things we will not be interested in our present course, as they are fairly deep from an engineering perspective. In the next lecture, we shall continue with our discussion of periodic and aperiodic functions. And in that direction, we will provide a strong theorem which gives you a necessary and sufficient condition for the sum of periodic functions to be a periodic function in the special case when f and g are continuous. So, thank you.